Okay, let's pick up where we left off now, section 3, where we concentrate on Ohm's law in the series circuit. So you can see we're going to use Ohm's law to analyze the circuit, starting with the simple expression I equals E over R. So the first thing we need to do is reduce our total number of resistors down to one equivalent resistor. That equivalent resistor then becomes the total resistance of the two resistors R1 and R2 summed together. Once we have that value, 5 k ohms, we can insert that into the Ohm's law expression E over RT. Since we know that the applied EMF or the source voltage is 10 volts, all we have to do is divide by that 5K resistance total, and we end up with 2 milliamps of current through the entire circuit. That 2 milliamps of current remains constant through the circuit, but we're able to solve for the voltage drops across resistor R1 and R2, again using Ohm's law, but moving the terms around, so we're solving specifically for the voltage drops. So for the first one, voltage drop 1 across resistor R1 becomes the product of the total current times R1, which gives us 4 volts. The same thing for resistor R2. So you can see the 4 volts and the 6 volts sum to equal our applied EMF or voltage source of 10 volts. Okay. So now let's take a look at some relationships that are formed using Ohm's law and the direct, inverse, and direct relationships that we can see. In any series circuit, a greater voltage drop appears across the largest or greatest resistance. Okay, so that's a rule of thumb that you can use to look at a circuit and try to quickly determine what the values are and if they're valid. So we can see here by forming ratios R1 over R2 from the previous circuit, we look at that previous circuit R1 and R2, we can say that the voltage ratio of V1 over V2 are equivalent. We can do the same thing then, since V1 by the total EMF is equal to R1 by the total resistance. So in this case, what it's telling us is it's giving us a proportionality or a percentage value. Since R1 is 4/10 or 40% of the total resistance, we can quickly look at a circuit and say, well, if 4/10 or 40% of the resistance is formed in R1, the other 60% must be formed in R2. So you don't even really have to solve this expression. You just know that by inspection that it's true. Let's add another resistor. In this case, we're going to look for a series of unknowns. We know the applied EMF, 12 volts. We know the voltage drop across resistor R1. We know the value of R2, and we don't know anything about R3. So how do we go through to solve for these unknowns? V2, V3, R1, R3, and RT. So if we start with the total resistance, we can say the total resistance then is equal to the total applied voltage and the total current in the circuit. Well, the total voltage and the total current in the circuit were given to us, 12 volts and 3.78 milliamps. So we solve for the expression, R total, and we get 310 ohms as the sum of those three resistors, R1, 2, and 3. Now I can solve for resistor R1 since I know the voltage drop across the resistor given 2.73 volts, and I know that the total current through the circuit, 38.7 milliamps, gives me a value of 70.5 ohms for R1. Now solving for the voltage drop across R2, again, since I know the total current in the circuit, I can solve by just multiplying, taking the product of the total current times the value of the resistor, 100 ohms, and I get 3.87 volts dropped across R2. Finally, I can solve for V3 by using Kirchhoff's voltage law. Kirchhoff's voltage law says that if I know the total EMF, I can subtract the other two known values, V1 and V2, from the EMF, and I get 5.4 volts. So the last step then is solving for the resistor value R3. Now that I know V3 and the total current in the circuit gives me 140 ohms. So we're using combinations of the laws as we're learning them. Ohm's law, the different variations of Ohm's law mathematically, and Kirchhoff's voltage law in this case. So in a parallel circuit, it becomes a little more complex. Again, in parallel circuits, it's sometimes easier to use conductance instead of resistance. So if we take a look at the circuit, we're given two values of conductance and the total current in the circuit. Notice our symbol has changed over here from a battery to a current source. This is always the recommended representation for a current source. So we can solve for the total conductance in the circuit by adding the two conductances, and we get 5 millisiemens of total conductance in the circuit. Now I can take the voltage expression, writing Ohm's law as a voltage then equal to the total current and the total conductance, and solve for the value of the voltage, even though it's not given over here. It's given as a current source. Okay, so now we've applied for the solved for the applied voltage. The next thing I'm going to do is, again, relying on Ohm's law, V over R, or the equivalent V times conductance, G, I can solve for each of the currents through G1 and G2 by using that relationship. Now, knowing that I've got 2 volts across each of those conductances, I end up with 4 milliamps and 6 milliamps of current. So now I know my branch currents going through G1 and G2. Finally, I can solve for the total resistance in the circuit as the inverse of the total conductance, 5 millisiemens, or 200 ohms of resistance. So you see, we're using different relationships to solve for our unknowns. A little more complex representation, we've got a parallel circuit buried in a parallel circuit. So you need to always stepwise solve for the parallel branches first, reduce them so that you can solve series, and then finally a parallel. So in the green box, you can see we've got a parallel expression. We're going to solve that first. R2 and R3 are in parallel to form that equivalent resistance we're going to call R sub A. R sub A then is equal to the inverse, or the conductance relationships, 1 over G2 plus G3. So if I solve for 3.9K and 5.6K ohms respectively, I get 256 microsiemens and 179 microsiemens as my values. I can simply sum them in this denominator and then take the inverse of the sum, 435 microsiemens, to get 2.3 K ohms. That forms that entire relationship or equivalent in the box. So now the next step is the circuit simplifies to this representation, where I now have R sub A and R1 in series. Well, that simply becomes the sum of the two. So when I sum those, I get an equivalent resistance of 3.3 K ohms. So now that equivalent resistance, 3.3 K ohms, or R sub B, is in parallel with R sub 4. So now I need to go back to my relationships in conductance. I'm going to sum the two conductors as 1 over the conductance sub B plus the conductance of resistor R4. Doing the inverse math, I end up with 303 microsiemens as the conductance for RB and 100 microsiemens as the conductance for R sub 4. and get a total of 2.48 K ohms. I can take that value, plug it back into the current relationship for Ohm's law, knowing that it's 12 volts applied. The total resistance now, as we can see over here in our equivalent circuit, becomes 2.48 K divided into 12, or 4.84 milliamps. So that's the total current in the circuit. Now if we want to go back and solve for the currents through each of these, I've got a current that hits this node, goes through R1, splits into two values, goes through R2 and R3, and back here where it joins up with the leftover current from R4 and becomes our total current back into the source. So in this expression then, we look again at the proportionalities. I2 divided by I1, or if we move it to the other side, is equal to G2 divided by the sum of those two conductances, G2 plus G3. When we go and multiply and divide, we end up with a current through resistor R2 as 2.14. So if we look back here, here's R2. In this branch, we just solved for that current that went that way. Now we're going to look at I3. I3 says we can use Kirchhoff's current law to find its value by taking the difference in the known current, I1, and I2, and we end up with 1.49 milliamps. Okay, so we've got those values. Now we can solve for each of the respective voltage drops, voltage 1, voltage 2, and voltage 3. Voltage 1 becomes the product of I1 and R1, or 3.64 volts. Voltage 2 becomes the product of I2, R2, or 8.63. And then finally, since the voltage across V3 is the same as the voltage across V2, let's go back and look at it. There it is. That voltage and that voltage have to be the same. We end up with 8.36 from the term that we solved previously. So we've taken what looked like a complex circuit, boiled it down into parallel and series relationships to end up with the simplified circuit of the total resistance and applied voltage. This will become important later as we look at and use something called Thevenin's theorem. So that finishes chapter 11.